Module 9 introduces wide area networks, but now we expand beyond the closet, beyond the buildings. In this module, we'll see more elements of wide services and introduce the concept of routing and how things communicate in the intranet and the extranet, and some of the WAN technologies for internal networks and wireless networks, and just networks in a large scale. So in a LAN, you have nodes are connected to each other. How they interact and they share information with each other. And we have introduced the concept that we have a router. The router is the one that connects those LANs together. But routers also allow you to connect enterprise networks with another enterprise network over a wide area. It could be within your county. It could be within your country, your state, or your country, or to multiple countries. So to do this, it obeys the same OSI model. You have to obey all those models. It's just that you layer 1 and you layer 2 are going to be a little bit different the way things are connected to each other. And now in these WAN technologies, and you'll have layer 3 protocols that you have to rely on to route your traffic from one network to another. These connections are usually privately owned, and is normally you lease those lines from the telecom companies. So you have what is called the network service providers. They could be AT&T or Verizon. I never heard of Spectrum, but the book has it. Comcast, also Crown Castle. The college uses Crown Castle, which is a spin-off from FPL. That FPL happens to have fiber all around Dade County. And so they embark into data communication with that fiber they had. They took advantage of that, and they started with FiberNet, and then FiberNet became Crown Castle. So, but all these fibers are actually leased. You pay for their services. So this network can span a few miles, tens of miles, or hundreds of miles. When you go hundreds of miles, you're not just talking about your WAN, the wide area network, but you're talking about the MAN, the MAN, for a metropolitan area network, which it includes, a larger area. So when they provide this service to you, you'll have the entry point equipment, or what is it on your DMARC. Remember, we spoke about that DMARC, right? So companies sometimes will provide their own equipment. For example, your home network, the companies will provide you with a modem, or you can buy your own modem and connect it to their equipment. So that's how you get the signals to them. So there's two types of equipment you will see. The DTE, which is the data terminal equipment, which is the customer's endpoint on that WAN area. And the data communication equipment, the DCE, which is the carrier's endpoint on that WAN area network. So the provider is a DCE, and your side is a DTE. Sometimes this equipment, if it's on your premises, it will call the CPE, the customer premises equipment. That's in variation for the DTE. And that equipment is also called, where that equipment is installed at that point is called the DMARC. So the demarcation point is where they deliver that equipment, and their responsibility ends at that point. So they provide the connection, it goes to your DMARC, and out of the DMARC, then you take that connection into your own equipment. So this image gives you a better description of that. So you have the internet that goes to the ISP infrastructure that is owned by them, and they will install a DCE, their piece of equipment, and then it goes into the DTE, the data terminal equipment, which is your customer side, and then that will feed your internal network. So that entry point is also called a handoff. That's where they hand off the equipment to you, or the connection to you. At that handoff, that's when your company will take it and distribute that into your network. The provider might include a NIU, the network interface unit, right, to connect them into what's called the local loop on the network. You may have some line drivers, which is kind of a repeater just to recondition the signal. or you can have a CSU DSU. The CSUs DSU were more like a traditional services for like T1s or T3s. T1s were digital services with 24 channels that they have been kind of disappear little by little. Because the T1 will provide you with a 1.5 megs, and nowadays 1.5 megs is nothing. Even your phone has 100 times the capability of a T1. So this the CSU DSU, which is a channel service unit, data service unit, it was just a way to convert from a more like an analog signal to a digital signal. And that will be delivered to you from your ISP or your internet service provider. So as we mentioned before, routers would join two or more networks, right? When you have a network, a LAN, LANs can connect to a switch, but switches cannot route traffic. You cannot connect two LANs through a switch. So you need to go to a router that goes into a layer 3. Switches work on layer 2. Remember, with MAC address, that's all they know. Now, layer 3, they know about IP addresses. They know exactly those same IP addresses, internet addresses that you will see on any web server or any service out on the internet. So routers will connect networks together, LANs and WANs together. Routers, remember that they work on layer 3 and they're aware of layer 4. Layer 4 because they know those TCP ports. If you want to go port 80, 443, if you want to do port 23 or any remote desktop or 389, those things, the router knows about those ports and they keep track of what kind of communication you're trying to relay from one service to another or from one client to another. And also the route, meaning that they know how to get from point A to point B. They have internal tables. They share tables of information of what do they each other know, and they determine which is the best way to get from one place to another to route your traffic correctly. Case in point, if I go on the expressway and I open my GPS, the GPS routes my traffic. It tells me which is the best way to get from point A to point B. If I should go through this to the regular roads, or should I get into a highway, or which highway to pick, which one will be faster, which will be the shortest one. So all these different measurements the GPS can give you. So routers will do the same thing. They will determine on a certain criteria, right, how to route your traffic. It could be based on distance. It could be based on throughput. It could be based on hops, how many hops you get there. You go through 3, 4, 7 routers rather than going to 3 routers. So, and there are different measurements that we'll see on routing. So routers do a lot of work. They filter broadcast transmissions because they are the endpoint for that broadcast. Remember, when you do your networks, you have a gateway and you got a broadcast IP address. That broadcast domain stays within that area. So the router prevents that one, your gateway, from broadcasting that into the other networks. It will support local and remote connectivity. That way you can get into the router and get statistics, get reports, get problems. It can generate also alarms. There are many other protocols that we'll see later on where you can actually monitor the status of your network or the status of your router, or if anything happens to fail, so you'll see it there. And of course, the fault tolerance. With the fault tolerance, that's when the router has multiple ways to get from point A to point B, and is able to determine and send you traffic the best way. And that is done by the routing protocol. You don't control that. You can choose which routing protocol you want to use, but once you choose that routing protocol, you're bound by the mechanisms that routing protocol will use. There are different ways to name these routers. So it's like a category. You have core routers or internal routers, interior routers. That's what you have within your network. Here they mention autonomous system. Autonomous system is a identifier for a BGP, a border gateway protocol routing. That anybody that talks on the internet needs to talk BGP routing. I will get into how BGP works, but that's what they refer here with autonomous system, because each system has to have its own autonomous system number that identifies your location. Miami-Dade has the AS19899. I mean, I don't know who the other ones are, but at least we are allocated to that, and we are the only ones in the world with that number. So when they're looking for that AS number, that belongs to Miami-Dade, and it routes traffic to us. So we have edge routers or border routers. Border routers, of course, is what sits on the edge of your network. So that's what it's called a border router or edge routers. And those are the ones that will connect your autonomous system with an outside network. Autonomous system because now you are within your own network, you're completely autonomous from the rest of the internet. And then border routers or edge routers are the ones that connect you to the world. Those are then you have the exterior routers, but those are the ones that are outside your organization. Those could be your provider router. So that provider will be called an exterior router because it doesn't belong within your enterprise. It doesn't belong to your network. So this is an example of autonomous systems and how the routers are named and they're connected with each other. Let's assume that on the left you got Miami-Dade. So you got two core routers and one edge router. That edge router connects to my ISP, my internet service provider. That goes to another service provider. Those are exterior routers because they don't belong to my network, my autonomous system network. And then it connects to the network on the right. Like let's say that's FIU. So FIU has three core routers, and one of them is the one acting as the edge router. And those four routers could be exactly the same routers. They don't have to be different, or the edge router doesn't have to be a special router. If it carries a lot of traffic, yeah, you make it into a bigger router, but it's just another router, and it just happens to sit at the edge. In this case, you have only one connection to the internet, so it shows only one edge routers. In many cases, you may have multiple edge routers, at least two, so you can have some redundancy. Miami-Dade College does have two edge routers that connects to the service providers, and each router has multiple connections to provide redundancy at the ISP side too. So I don't connect to just one single ISP, I connect to multiple ISPs. But this is the whole concept of core routers, edge routers. Those are all internal routers, and then you got exterior routers, which could be your provider. So when I talk about routing tables just is a database. It's a table of information of what your router knows, right? If I'm within Miami-Dade College, my IP address space is 147.70.0.0/16, meaning that we own anything on that 00 space. Everything that starts with 147.70. something belongs to Miami-Dade, and we distribute those IP addresses throughout the campuses. So all the routers that we have share the routing information. They said, hey, I am North Campus, and I have 147.70.200, 201, 202, all the way to 210, and by the way, I jump into 232. Well, 232. And then Wilson Campus says, okay, I am also part of the 147.70, and I have all the my routes are 147.70, 100 to 101, 105, 110, 115, and it starts in the hundreds. So they share all the information. That way, the North Campus knows when they're looking for a 147.70, 100 and something, it will send the traffic to who? To Wilson. And if Kendall has the 147.70, 40s, 20s, 30s, 80s, then all the traffic will be routed to Kendall. What happens to the traffic that is not 147.70? Well, the routers will have what is called a default route. When they don't know where to send the traffic, they'll send it to one specific IP address. So for the most part, the rule of thumb is that you send it to your border router, because if you don't find it inside your network, chances are it's an outside network. So we'll send it to the outside. I will say send it to my border router, and the border router has a way to connect to the outside and say, oh yeah, let me find that. Because if I am at another campus and I said, hey, I need to connect to www.google.com, the routers look at their table and he goes, not on my table. They can check on the Wilson campus table, shared table, and the Kendall campus shared table. He goes, nope, not here. He goes, okay, so let me send it to the default route, which is the border router, and the border router will make the decision that where to send it. If you have multiple connections, you'll decide which connection to go to. But that's how the routing will work. They just find a way to deliver that traffic. Similar to this, you have LAN A, B, C, and D. So router C says, hey, you know what? I have LAN D that is connected directly to me, is directly attached. And also LAN C is directly attached to me. So I know how to connect to those networks, and I'm the router for those networks. And then router A, of course, goes to LAN A, and he has a direct connection to it. He goes, hey, it's on me, and I know how to where LAN A is. And likewise with LAN B and router B. So when router C wants to connect to LAN A or LAN D, LAN D as in David wants to connect to LAN A, then he will send it to the router, and the router goes, okay, I can send it to router A, which is router A has a direct connection to LAN A. But also, if you notice, router A would advertise, they will do advertisement. So I'll advertise to router B and said, hey, I know LAN A because it's direct attached to me, but also there is a router called router C that he claims he has a connection to LAN D and LAN C. So he shared that information. So now router B knows that. And router B, in case, does the same thing. You say, okay, hey, A and C, I know LAN B, I own LAN B, it's local to me. And I also see that A is connected to me, and it will send whatever information router A has to router C, and whatever information he gets from router C goes to router A. So see how everybody knows everybody, and each table is completely shared. The routing protocol, what we'll do, let's say on LAN A. So LAN A says, okay, I know I have a direct connection to router C, and I have his routing table. But also router B tells me that he can connect to C. But you know what? Since I have a direct connection, I'm going to prefer that connection. So it will always route A to C directly if I want to go through that LAN, LAN A to D. But if that connection fails for whatever reason, then automatically knows, oh, but I have a secondary route, is through router B, and I can still connect to LAN D because I have another path. So that's how they start to route. It's like if you're going on an expressway and you're going, I don't know, through US 1, and then there's an accident somewhere on US 1. It goes, hey, just exit on 87th Avenue and continue 87th Avenue north until you hit Coral Way and then make a right. You get through those streets. So it will divert you because it doesn't want you to a place that is completely jammed or closed. So it will direct you through another. It knows another way to get there. So that's what routers would do. Now, yes, you can have a static routing and you can have dynamic routing. Static routing is when you manually enter all the information. Remember the example with router A, B, and C? Imagine you can enter all the information manually. Say, yeah, this is a router. How can you get to that? So you can do what's called static route. But normally, a static route is when you want to force the traffic to go in a specific way, you can force it by static routing. Dynamic routing, on the other hand, is when the routers learn automatically. They learn that path by exchanging information, those routing tables, with each other. So by getting that tables exchange, then the router can make a decision which way to go, and if something fails, it will find an alternate route to get to point A to point B, from A to B. But I can use a static router that says, you know what? I know that you have a best way to go this way, but I want to force you to go through a static route. The problem with static routing is that if something happens to that one link where you said to go A to B, you have to go this way. If that path fails, the router still has a static route. He cannot dynamically find another way to go from A to B when you have a hardcoded there that you have to go that way, and the router will obey that static route all the time. So that's the only downside of static routing. Now, if you have some routers that doesn't do well with routing protocols and all that, and it's a small router, a small network, then yeah, you can do static routing. At home, you don't need routing because at home, yes, you need a router, but everything goes to the outside. You don't serve anything inside. You have your computers connect to each other, but you don't have many services inside for them to be routed to multiple networks, unless you build something large. I mean, in my house, I built a wire network, a wireless network, and then I have a management network for the switches and the routers and all these things and all the other devices that I have. So yes, there's some routing inside between those three networks, but then when anything that has to go out to the internet goes only one way, one single path to get out, and then I can have anything else is not on my network. Let me put a static route. And in theory, you will have a static route, which is called, like I mentioned before, the default route. Is it says if you don't know where to go this way. That's the way out. You know, this is the connection that'll push you all the way to the your router, to border router where you have your ISP, and it will go out into the wild, see if you can find it there. But that's the only way only place that I will have a static route. Now, every device on the network, any device that connects to a network will have a route. Even the smallest device has to have some kind of route. Your gateway, that's a route. That it tells you if you don't know where to go on your LAN, if you're in the 147.70.40 LAN, and you're trying to go to something that is not within your LAN, what do? Go to your default gateway, right? Your default gateway is hopefully the .1 IP address, and that one is a route to say if you want to get out to your network, go that way. So that's where you put the .1. That's where your computer will know how to go. Now on Windows, you can do route print, and route print will show you which is your gateway and what are the routes you have on your network for any known networks inside your network. Cisco iOS, you do show IP route. Linux system, just simply you say, put the command route, and it will show all your routes. I guess the Mac OS might be the same thing. If you go to a terminal and you type route, it will show you the routes that it knows. Every time you connect to something, it will create like a route entry on your computer to just remember that, yeah, that was an outside network and I found it through the default route, and it will be through there. If you connect through a VPN network, and you connect VPN to your employer, then more routes will come into your computer, because now your computer has to route either through that tunnel or through your regular connection, plain connection out to the internet, to your Comcast provider or something like that. When you create VPN, remember it's a tunnel, an end-to-end tunnel. So you don't want to go through Comcast. You want to go into that tunnel that's already established between your computer and your endpoint, and route through there. So when you connect VPN and you do route print, you'll see a whole bunch of IP addresses that are injected by that VPN software into your computer. Now, depending on which routing protocol you're going to be using, there's different metrics that the routing protocol will use. It could be a hop count, bandwidth or throughput, delay or latency, the load or processing on the traffic. Never seen routed by MTU, but yes, it could be by the MTU. Remember, the maximum transmission unit is the maximum size packet that you can have on a communication. You can have jumbo frames where is more than 1,500 bytes, but the MTU can determine that. Some other protocols we use what's called a routing cost. A routing cost is not how much it costs you to use a circuit. It's basically a value that you put to that route, and it says, if you go this way, the value is 10, and you can start counting increments as you go along through different paths. And in other ones, you have 1 or 2 or 3, 5, 25, whichever number you want. Another ones, it depends on the topology of the network. So, but we'll see some of the routing protocols and how they're being used. So your routing protocol is going to choose which way is going to route your traffic, and that can be based on different criteria, right? The administrative distance is a number, like say, usually like a cost that you can assign. So that number, it tells you, which is the best way to route out, and that you can manually do that whichever you want to do that. Convergence time is the time that the routing will take to change when something gets modified on the network. If a connection drops, if a router goes away, or a link dies, then how fast can this network recover and learn the new route? So it's just to see how efficient that it is. Some routing protocols are faster than others. It depends on the outage. So it depends on how fast this thing can go. And the overhead is how much of power is required to get that information and get processed from the router and get a final result for you. The final decision. That how this thing can be taken. So that's just the overhead on the router. So some of these protocols can be either interior gateway protocols or exterior gateway protocols. Um, Exterior gateway protocols, the one that is used is BGP. Anybody that wants to talk on the internet needs to talk BGP, Border Gateway Protocol. That is the if you want to be on the internet, that's what you need to have. The internet runs on BGP. That's where you get your autonomous system number to identify you. But if you want to connect like as an independent site on the internet, you need to have BGP routing for that exterior protocols. Now on the interior protocols, that's what you run inside your network. You have a choice of different routing protocols. There used to be the RIP, the routing information protocol. It was a distance vector that it will find the calculations based on that distance to the destination. But those were slow, were very limited. Even when RIP, RIP, the routing information protocol v2 came out, it kind of gave it like an extension to the version 1, but it was not efficient. So the link state routing protocols are more efficient, they're smarter, and they can work independent, from your network. And then that's where it starts to share information between other in a way, creates a map of your network to find the best path. That's when I said that, remember that router A advertises to B and C, and router C gets information from A and B. So start creating this map of the network to make the decision which is the best way to route the traffic. So there's a couple that use link state. That's we'll get into those. The OSPF, which is open shortest path first, and ISIS, intermediate system to intermediate system. So ISIS is very efficient. I like that ISIS. I've used it, but the college is actually runs on OSPF. There is EIGRP, which is I think that's a proprietary from Cisco, or it was made by them. It was like an advanced distance vector protocol, and but since Cisco is the one that made it and all that, it's not widely used. But there are different type of routing protocols that you can use. Okay, so here you see your internal routing protocols. You can have RIP or RIP-v2, OSPF, ISIS, or EIGRP, which is that's the one that I said that it was done by, it was a Cisco proprietary. That's enhanced interior gateway routing protocol. So it's an interior gateway routing protocol. Then on the outside, on your exterior routers, you see that to connect to them, you had either BGP or EGP for the exterior gateway protocol. So like I said, but anything you run on the internet, then you have to run BGP. BGP is the routing protocol to go. But inside you can use anything. You can, like I said, RIP1, RIP-v2, it's just way too old. Nobody uses that. The most that you will use most likely will be OSPF, ISIS, or if you're hardcore Cisco, EIGRP. So OSPF, the open shortest path first, is a link state protocol used for interiors. You cannot use that on exterior protocol. Remember, that's only for interior. It can run on large networks, like the Miami-Dade College runs on OSPF. It has no hub limits. RIP was one of those that was, fell short on that. It has a complex algorithm. It has what's called the Jastra protocol. the digester algorithm that is the one that uses to compute, which is the shortest path to get from one place to another, from A to B. It's a shared data. That's when all those databases get exchanged between all the routers, all across all the routers. It's a low overhead. It's a fast convergence. BGP can converge fast within a few seconds. If something drops, OSPF will converge within seconds to find a new path. When a new one comes in, it takes also like 2 to 3 seconds for that tables to get learned and propagate through your network. It's a very stable a network, routing protocol. And that also helps to prevent routing loops, because when it learns multiple paths, it will just use one of those. It will not use both. OSPF and all these routing protocols, it will always use one path to go from point A to point B. Even though it has an alternative path, it will use only one. If it uses the other one, it creates those routing loops. Remember that we mentioned that the spanning tree will take care of. So to avoid those routing loops, OSPF will actually learn and decide that, okay, this is the one path that is the best, so I'm going to use that one. If it fails, it can compute another one, but it will not keep both. Okay. Multi-vendor routers, yeah, the OSPF is supported by almost everybody. It's a very since it was it was open source. So that's what's called open shortest path first, but because it's an open source, so anybody can use it without any reservations. And then you got ISIS, intermediate system to intermediate system. It's very similar to OSPF. The only difference is that on ISIS, you have to configure like a site ID. So each router has what is called a site ID, and then it will, when it propagates information, the other routers will learn that site ID, so identifies a specific router. It says here that it's for core routers only, but you can actually use ISIS anywhere. It's just that OSPF has mechanisms to create certain areas on the network where you don't get all your routes, so you can filter what routes you want to get on that area. For something like a remote site or something like that, you can do that with OSPF. ISIS doesn't have the mechanism, so but it still can be used in any area. Then the EIGRP, that's I guess this is the one that Cisco has. So it's more like a hybrid protocol. It's fast convergence, low overhead. Is less intensive than OSPF, but it runs only on Cisco routers. And if you want to traverse multiple routers like that, then it becomes cumbersome. So it's easier to stick to some standards like OSPF or ISIS. And finally, we get to BGP, Border Gateway Protocol. That's the one that I said that it's the exterior gateway protocol that you have to talk on the internet. That's the only protocol that you have to use to connect to the internet. And it has to have that autonomous system number, so it's an AES number. It is a path vector. It's efficient. It can be customized. And BGP is basically a hop count algorithm. I mean, it's all based on hop count. It doesn't measure how fast a connection is or how latency you have. It kind of computes most of it, not everything, but most of it based on the hop count. Hop count means how many routers I need to traverse to get from point A to point B. If I go through one path and that has 20 routers, but I find another one has only 18 routers, so I will choose the 18 router path because it's less hops. But sometimes that is not the best way to get there. So, but it is the most efficient way to do it. So it's a hop count. Now, on networks, for large networks, you want to have some kind of redundancy. Like I mentioned, Miami-Dade College has 2 border routers to connect to 2 ISP connections. So you can have what is called active-active redundancy, where both of them are connected constantly, or they're active-active. They're both passing traffic at all the times, and they work together. BGP allows you to do that, so you can have active-active with no issues, or you can have the active-passive, where one is active and the other one is just sitting there waiting to be turned on or have traffic forward to it to forward the traffic. With the active passive redundancy, what sometimes what you can do if the active one has some problems, so you need to do some update or something, you fill over to the passive one, make that one the active, then you go back to your active one, your previous active one, the original, that is now down, do the updates, do whatever you need to do, you reboot it, fix whatever you need to fix, add, remove hardware, something like that, and then you fill over back in. You go from the secondary to the primary, and then you're back in business. So for the most part, you'll probably have always like an active scenarios. Then there's another type of redundancy where you can have what's called a virtual IP address, where you share an IP address within, let's say, two systems. The standard is called VRRP, a virtual router redundancy protocol. And that also, what happens in there with any of these protocols is let's say you have an IP address that is a .1. So that's your VIP, that's your virtual IP address. So you configure the other two routers to be the .2 and the .3. The 147.70.40.2 on one router, 147.70.40.3 on the other router. But then they share this one IP address. So one of them is going to be the active one. So on this scenario, you have active passive. So one of them is receiving the traffic, the one that is actually the massive for that one, that even though it has a .2, he owns, or he's the manager of the .1. And the other one is just on standby with a .3 IP address. If the other one fails, then this one, the .3, can become the .1. So you always have one single IP address, that virtual, that any of the two can respond to it. The same protocol is on Cisco, but it's called HSRP. It's a hot standby routing protocol. And also the GLBP, the Gateway Load Balancing Protocol, which is also from Cisco. You can use that as a virtual IP address. So on your WAN connection, your wide area network, you can have a broadband. Broadband is shared to multiple customers. Broadband also means they have multiple services, right? Your bandwidth is asymmetrical, meaning that your download speeds are faster than your uploads. Have you seen on your Comcast or even your AT&T that if you do downloads, it's fast, but the uploads is slow because they don't expect you to serve any content on the internet. You're going to be ingesting more. You're going to be downloading more than you're going to serve out to other people. Those services are called best effort, meaning that they will just provide you, the best way to get the fastest speed that they can offer you. They can offer you 100 megs, but doesn't mean you will get 100 megs. You will get the best effort. They'll get 70, 80, 90. You're still close. It's the best effort. And you can have a dedicated internet access is dedicated to you, and this one is symmetrical. Symmetrical means that your download and the upload are symmetrical. They're the same. This is more for like a business, right? And on this one, of course, if it's a business, most likely you're providing some kind of content to the outside. It could be your company's web server, your email servers, and things like that. If you have your own DNS servers, then it has to be served to the outside. So that's where you want to have the symmetrical. So you have the same amount of bandwidth inbound as you can have the outbound. All right. So now I can't believe, I don't understand why. If this is a new book that was published recently, I think this is from like last year, the author decided to still keep DSL. You cannot get DSL anymore. But anyway, that was a digital subscriber line, right? It was for like home networks. It couldn't get long distances. You needed repeaters in the middle. And the distance between you and the CO, which is the central office, the provider, that's called the central office, depends on that distance. That's the throughput you will get. In my house, I remember when I had DSL, even though the it was advertised at 1.5 megs. I could never get more than 900, 930. I could never get over 1,000, even though I promised 1,500. I couldn't get any past 900. ADSL, well, DSL connection is a type of modulation that would actually mix your voice line with your data line. So there were two different frequencies working in there, and each one has its own specific frequency to work, and that's how they were able to send the traffic through one pair of wires. So back in the day, they had an ADSL, which is a asymmetric DSL, to give you better downloads. Then they had the VDSL for very high bit rate. And then the SDSL, which is a symmetric DSL, that was promised to businesses up to like 2 megs. It's like, who works right now on 2 megs of traffic? Nobody, not even your phone, not even at the worst location on your phone, not even when you are like way out on the beach and you're away from the tower. I think you will get more than 2 megs of traffic, unless you go on a boat out of the ocean. You get to a point that, yeah, you lose it. But yeah, ADSL was very, very slow. Like I said, I still don't understand why it's still this in the book. So now cable broadband is still alive, right? Comcast still does that. It is delivered through a coaxial network. It is a broadband meaning that you have multiple services. You have your TV, your network, internet, and you may have your phone also delivered through that. So that's what's called broadband. You can have multiple services in there. You'll use a modem with specifications that's called DOCSIS, the data over cable service interface specifications, and it depends on which DOCSIS version you have. They will be faster the speed. I mean, yeah, you can get 70 megs. But if you got a DOCSIS 4.0, they can give you up to 10 gigabits of speed and 6 up and 10 down. Cable modems are shared media, meaning that when a line comes in with specific bandwidth, it actually goes into like a splitter, and it gets split through all the clients within your area, your building, your floor, your block. So there are times where the cable broadband gets really slow because of that. Some of this is delivered through hybrid fiber coaxial. So the provider will bring not a coaxial cable all the way from their offices into your area. They will bring it in through fiber, and right at the end is where they have a converter that will convert your fiber to coaxial cable to deliver to your home. Remember that coaxial, those are electrical pulses, is electricity they have to put in there. So electricity degrades as it goes through distance, especially on a coaxial cable. So it has to be close to your home, that coaxial. So you'll use fiber to coaxial. So that's how it works. You have your head end, which is your service provider. It goes through many distribution hub. It could be a fiber ring like that. Then you got fiber going to the node, and the node will convert that to coaxial cable. Of course, this node has to be power, so you can convert that fiber back to the fiber signal, the light signal, to electrical pulses. On the nodes, that's where they're all going to all the customers to the cable modem, and that's the one that's the share media, because you're sharing that fiber going to the node. And it depends on the speed that you have. That's how much throughput you're going to get to every customer once they connect to a single node. So broadband uses a cable modem. We mentioned before, modem stands for modulation demodulation. So the modulation demodulates the signal, right, to go in and out your connection. And normally your cable modem is attached to a router. So that small router, or it could be a multifunction router where you have your Wi-Fi or your wireless access point and your router built into one. You might have a small firewall built into that too. And it routes your traffic, and it might have multiple ports in the back acting as a switch. So now you have multiple ports going to the same LAN on the internal network. It goes through the router, and the router connects, with a cable to your cable modem, a regular Ethernet cable, and the cable modem converts that Ethernet into cable, the cable broadband to take it into their network. So this is more for even for a small office. It will work for homes. It's perfect. Um, it provides a dedicated and continuous connection. Yeah, if you've been a Comcast customer, see how many outages you have through the year. But they're supposed to provide you a continuous connection. And like I said before, it's a shared media. So it's a medium. So that happens that sometimes your throughput goes up and down, and also there's some security concerns. I don't know if there's still people do it, but there's some point people were stealing the modem's identifiers from other customers, and they will reprogram a modem, plugged it into the network, and the network was basically not aware that that same identifier was connected in two or more places at the same time, and anybody can connect to a network. So I don't know if it still is possible, but at one point it was very popular. People actually, in a way, stealing, well, not in a way, actually really stealing the signal. Uh, but that's because it's very, very insecure. So new services are provided through fiber. So you get fiber to the node, fiber to the curve, or fiber to the building, or fiber to the home. That is part of this metropolitan optical networks. It's an optical network going, through the whole city and providing fiber to that. So many people already have fiber, what's called fiber to the curb, or fiber to the home, where they bring the actual fiber all the way to your home. Or fiber to the curve is that they bring it to basically to your sidewalk, and from there they can bring it on a cable. But it's such a short distance that connections of 1 gig are easy to transport from the curve to your house or to your curve to your building. And of course, you get fiber to the home, that you get fiber all the way to your home. So if you have copper outside, remember, any cable that you have hanging outside is a big antenna. So any lightning or anything like that, it can fry those cables. So fiber to the home is a lot more secure, and nobody actually can tap into that. So it's very secure. In my area, when I used to get that 900 meg DSL, now I'm able to get fiber to the home, and my service is one gig. And when I clock it, yes, I do get not fully 1 gig, because that's the best effort, but it gets close to go to 1 gig. But that's the most cleaner, efficient, secure way to get faster speeds to a home or to a business. If you have a business and you get 1 gig, also that will give you a awesome connection for any small to medium sized business. All right, so this diagram, you gotta read it correctly. The red is fiber, light communication, and the blue, it's copper communication. So when you get a fiber to the node or fiber to the curve, they're similar. It goes fiber all the way to the curve, and then from there it's taken to your home, your building, or your business through copper. And then fiber to the building is when they bring it all the way to your customer. I mean, here it shows just a little piece of the blue, but there's no transition there. So, but like in my home and other installations that I've seen, the fiber is all the way. That NIU, the network interface unit, is actually installed inside my house, bringing the fiber all the way from the ISP. From, in my case, it's AT&T, but it's brought all the way inside, and it has to have power, because then that NIU is going to convert the fiber to copper, so I can connect that into my router. Now, when you go beyond your premises, then you need to have some lease lines, right? For dedicated bandwidth on fiber connections. So you have symmetrical, yeah, you get the SLA guarantee. SLA is a service level agreement. Service level agreement is what determines, it says, okay, we'll give you 99.999 uptime. So they guarantee that you're always going to have a service. And have a dedicated bandwidth. That bandwidth is not shared with anybody, and when it's fiber, it's completely secure because it's just to you. But that's when you lease it from providers, either to give your internet or to get connections from one side to another. Case in point, Miami-Dade has lease lines that go from campus to campus. The only connection to the internet is downtown. That's where we have all the connection to the internet. All the other sites, they connect with each other through lease lines. So Kendall connects to West Campus connects to the North Campus connects to Medical Campus, Medical connects to Wilson Campus, and Wilson Campus connects back to Kendall. So it's like a ring. Then we have like a leg out that is for Padron Campus. It goes Wilson to Padron, and there's Padron to Homestead to feed Homestead. But Homestead also has a connection to Kendall Campus. So it's like a whole ring, and all that is through lease lines. So there's always changing on the pricing and the services and all that. Everything is always improving, and the charges actually are based on distance on throughput that you're getting. Another popular service is the MPLS, multi-protocol label switching. That enables to layer 3 protocols to travel over layer 2 protocols. It's sort of like a cloud service that you connect to a network from your provider, and then within the network, they will connect you, kind of like they will route your traffic to connect to the point A to point B. With MPLS, there's two types. The MPLS, and also there was one from AT&T. It was called Metro Ethernet. Metro Ethernet, it was just like another flavor of MPLS, but it was pretty much the same type of technology. With MPLS, you can say, okay, at this location I want 1 gig, but at this location I want 5 gigs, and at this location I want 10 gigs. So you can have a multiple type of the throughput on each location, right? And then you connect to their equipment. When we have lease lines, the equipment from one location connects to the other location directly. So as you're using lease lines, because that line, that circuit is all yours. But with MPLS, it goes into this mesh network, and then you route through that mesh network. Mesh meaning that all the routers are connected to each other, and there's multiple ways from multiple sites, right? So MPLS introduces what's called a label. So it will label your traffic, and then once that traffic it gets into the network with that label, it gets routed to the destination where you want to have it. So the two sites need to basically kind of like point to each other. So I said, hey, point A, I want to go to point B, and point B says I want to go to point A, and it labels that traffic in there. And then at some point I said, you know, I don't want to go to A anymore. Let me go to point C. So B goes to C, and all you need to do is change that label configuration. And then on C location, say, okay, now C is going to talk to B, and B is no longer talking to A. So it's very scalable. It's very flexible. You can create those connections from anywhere to anywhere within, you can have, let's say, 5 locations going to the MPLS network. So you can create whatever connections you want and all that. Too bad the author decided to take out frame relay out of the book. I would have actually kept frame relay and take out DSL. Frame relay was a network that worked also sort of like MPLS. A lot of the technologies that you see in MPLS, it is actually based on frame relay, and frame relay had that concept of a label. That you identify one side and you want to say, I want to talk to this other side. So they both have the same label, so they will talk to each other. So it was very efficient, and that's why MPLS kind of like inherit some of the that technology. It was called the number was a DLCI, a digital link circuit identifier. It was digital link circuit identifier. So the DLC, I said, hey, I'm DLC. I have DLC 10 on this location, and then point B said, okay, I'm DLC 10. So that frame relay inside will propagate 10. It goes, hey, 10 needs to connect to 10. So they will find each other, and they will find a path through that mesh network on how to connect. So that's why similar what MPLS does on today's networks. So this is a diagram that you see the MPLS. In this scenario, actually, all those LSR routers are connected to each other. There's like a mesh with all connected to each other, and the customer edge router will find that ingress point to enter that network, and it'll find the egress point to connect to my customer edge router. So the two routers, the two edge routers can talk to each other. That could be two sites, like I said, I don't know, campus, Wilson campus to North campus, and it goes through, an MPLS network, and then, but all those LSR routers are actually owned by your provider. You don't touch those routers. You don't have access to the routers. You don't see those routers. You don't even see how many routers are in there. As your network concerns, you enter that point of ingress and you exit on the egress point. So for your customer is one hop. You enter one point, exit on the other point, and you don't see what's in the middle. The MPLS will route everything internally, but it's completely transparent to you, to your traffic. So it's like I said, it's very efficient, very secure, and is redundant. If anything happens within that MPLS network, the MPLS domain, it will reroute automatically, and the customer will not even see any loss of connectivity. So now that everything is connected to the cloud, you can have a direct connections to a specific cloud. In this case, we got Amazon, AWS, or Google, Azure, Oracle, Salesforce, any of those. So your customer can be switched to any of those connections. What's called the colocation facility. Colocation facility is kind of like just a large provider that has direct connections to all of these networks. So you connect to what's called the fabric. It's called a fabric. You know how the fabric is a thread going, left to right, and thread going up and down, right? It's all interlaced together. So that's what's called a fabric. Because all these connections are interlaced together, and the colocation facility makes that connection possible. In the previous years, and a few years ago, what you had to do was to get basically from the customer a VPN or some way to connect directly into the Oracle network. We had that at the college. Or if you want to go to AWS, you had to create like a VPN and connect directly to Amazon, so you know that your traffic is there. But now with this Fabric services, you can go to your provider, and if they have direct connection to all those services, they can do that connection for you. We do have a connection to Oracle at the college, and it's a dedicated line. It's a 1 gig connection. We don't use the full gig. Only when we do backups, it goes to like 150, 200 megs, and it happens to be like at 2 in the morning or something like that. But during the day, traffic is very low, but we go directly into that fabric, so we don't have to have that VPN and relay on those technologies and that conversion to create the tunnel and then the encrypted tunnel, decrypted tunnel. This is a direct connection from the college to the Oracle network, and you can do that with any other. And like I said, this is all through a cloud connectivity on your colocation facility. Colocation, again, that's the main building in your town that connects to all these networks, and is one of those large providers. Here in Miami, we have a few. One of the largest is the Napa de Americas, which is downtown Miami. So another new technology is the SD-WAN, the software-defined wide area networks, and that one it's also a smart service. It simplifies a lot of the configuration. Is transport agnostic, meaning that you can have different type of connections or broadband lease lines, cellular, whatever connection you have, and the SD-WAN will actually manage those connections and connect everything together. So it doesn't have to be on a specific type of network. You have active load balancing, so it's automatic failover. So if anything happens, it's sort of like an MPLS. An MPLS, if it doesn't have one way, it will go to another one, but it will always route your traffic. The intent-based management is that you can actually control the bandwidth that you want for a specific applications or a specific type of traffic. So you can manage and in a way that you can limit or provide more traffic to it's a way to do what's called traffic shaping. Then now you said, okay, for this type of connection, for this type of network, well, I don't care much of my customers are getting into Facebook, so I'm going to lower the bandwidth on Facebook. It's still there, it's available, but it's going to be slow. But then if you want to go through CNN, oh, this thing is going to go fast. If you want to go to Google, it's going to go fast, but not to Facebook, because that we consider to be a low priority, so you can lower that. SD-WAN also provides zero-touch provisioning, meaning that if you have a new piece of equipment, you plug it in. SD-WAN will actually provide a basic configuration for this equipment to come up, and then you go in and continue configuring the network. It's a reduced cost because it provides, it simplifies the configuration or the management of multiple networks with multiple connections and multiple sites. The SD-WAN will actually manage everything there, especially with the zero touch that will provide everything, and new equipment will come in. It can save you time. So it's just new. This is new. We haven't used that at the college. We talked about it, but we haven't used any SD-WAN equipment yet. So here you can see how you can manage things through the SD-WAN. So SD-WAN, it says, okay, if you're sending emails, then send that through the 5G wireless network. Your phones are going to go through the broadband, and the MPLS domain is down or is not being used, so everything gets rerouted through the broadband and the 5G. So that's how you control that. So of course, everything will go through your MPLS, because that's the more reliable and better network. But if that fails, then I can route the traffic. I mean, phones do require enough bandwidth for the voice to go through, and the voice has to be delivered in fast because it's voice. You don't want delays on the voice. Whereas the emails doesn't really, you don't care if the email is delivered 3, 4, 5 seconds, even 20 seconds, even 30 seconds later. Who cares? It will get delivered. Just wait a little bit and you'll get it. So you can route that through much slower network like the 5G wireless network, whereas your phones and some of your data can go through the broadband, and that gets controlled through SD-WAN. So from my side, as a network manager or network administrator, I don't have to touch anything. SD-WAN will control that when any failure happens, to reroute the traffic the way I wanted it, the way that it was, how I configured and intended to do. So this section is kind of weird because it's called wireless ones, but I guess on the one what the author is referring to, it's more like cellular connection and also satellite connection, which is really covered very short, but at least it's included. So cell connection has become really important. It's part of our everyday life, right? And it all started with analog phone service, the CDMA. Remember the old phones? They were really bricks, big phones. Those were very, very, very reliable because it was like an analog signal. And that analog signal can actually travel far distances, so they didn't need that many antennas. And the phone needed a lot of power, so that's why they're heavy, because the batteries have to be heavy. But then, and that was kind of like the first generation. Then we started getting to the second generation, the 3G, 4Gs, and now we're in the 5G, where we start increasing the speed. 5G is supposed to provide us a minimum of 1 gig and 20 gigs. Right, downloads and uploads of 10 gigs. So for those who already have a 5G phone, I don't. I guess that you have experienced that speed. Now the problem with 5G is that the higher the frequency, the shortest the coverage. The same thing happens on the regular Wi-Fi. Remember, you got a 2.4 and a 5 gigahertz, and now with the Wi-Fi 6, you get 6 gigahertz. So the 2.4 gigahertz can cover a lot of area. A larger area, whereas the 5 gigahertz is more condensed and the 6 gigahertz even more condensed. So on the 5G, you're going to see that it's more and more antennas closer than the antennas you'll see for the 3G and the 4G. For those LTE services, the 5G needs more antennas. That's why they went around all the cities putting new antennas, because now the 3G and 4G networks were just not enough number of antennas, because the coverage is a smaller footprint. So most of you might know how cellular works, right? Cellular, you have an antenna that provides in a certain area. Of course, it's not a hexagon. Is more like a circle that they overlap each other a little bit. And on that overlap allows you to roam from one antenna to another. That's when your signal on your phone starts to drop to 2 bars, 1 bar, and all of a sudden you go full bars. That's because one antenna you're getting away from one and you get close to the other one, and then you get handoff. Now the MSC, your mobile switching center, is the one that handles that handoff. That's the one that is controls all that. It goes, oh, this car I don't see, or this phone I don't see it on this antenna, but it's showing up on this other antenna. Oh, there it is, and it's getting stronger. So let me move that communication from one antenna to the other so I can give you a better signal. Sometimes you don't get the handoff, and that's when you get a drop call because it doesn't get handoff correctly. And then the MSC, it will go to the central office, and the central office is just like any other provider that it will connect to the internet. And all these are digital signals. So digital, like I said, it's still that will communicate similar to the Ethernet. If you see your phone to your data network, you get an IP address, just like any other Ethernet connection, with a MAC address for the layer 2. So all those OSI layers for your data apply to cell phone communication. Now, satellite was one of my favorite topics in school. Satellite communication can handle voice, music, video, data. For many years, people were using DirecTV to get TV signals, hundreds of channels over one antenna communicating through satellites. The satellites have to be geosynchronous orbit, which is right above the the equator, right? So when you launch a specific height and right above the equator, what happens is satellite will get fixed to one location. That's why your dish network antenna or satellite antenna will point to one location, usually to the I don't know if you remember the commercials, as they said that for DirecTV you have to have a clear view of the southern sky. Well, because we're in North America. So in North America, to point to those satellites, you have to look to the south. So to south, because that's where the equator is, and you'll be able to tune to one of those satellites. Now, the satellite will have the transponder that will transmit that communication back to the Earth. But the satellite also has a downlink that on an Earth base, and that's the one sending all the information, right? Sending information, and then it will relay that information to the transponders to your location. You can also get internet. There's I can't remember VSAT or ESAT, something like that, that they'll provide Ethernet connections through those satellites. You can have a two-way communication there. So they offer high bandwidth. It just said like 10, 20 megs. It's not really high. The only ones that have the higher bandwidth, from what I remember, it was NASA, that their downlinks were 620 megs. I think was what it's called from the ATM times the OC12. It was 620 megs speeds that the NASA would have, and I guess that will be used for the military too. But for the public, those links are very they kind of slow, but still good enough. But it'll provide you with a good connection for voice. Perfect with 20 megs, more than enough. And it's all provided through satellite. But if you're in the middle of a desert or in the middle of a mountain, you put one of these antennas. Now you get internet and you get connectivity to the rest of the world. It will be a great, a great utility to have at your site. But it can be done. So the satellite will have the the uplink and the downlink. So you send information to the satellite, and the transponder will send it back. The satellite, of course, has to be on that geosynchronous, meaning that as the Earth rotates, the satellite rotates along with the Earth. So it doesn't go any faster than the Earth. It's just on a fixed location, and that is very tricky because it has to be on a specific height from Earth. So gravity doesn't pull it in. And it doesn't let it escape either. So it's kind of like a sweet spot where the satellite can be. And also they have to be spread out. There's so many satellites out there. It's like incredible how that is. Real estate is actually expensive to have a satellite located on that geosynchronous orbit. But it has to be in that specific one. If it's off that geosynchronous, what happens is that the sun has to wobble up and down. A GPS does that. The GPS satellites, they're not on the equator. GPS, they're on a different orbit. So those usually oscillate from north to south, and it's like a sync wave that it goes from north to south. And they're always rotating. But you can always get a fix from multiple satellites at the same time. So that's how you get your GPS signal. But for communication, direct communication, voice, data, and like that, it has to be on a geosynchronous fixed location. So the antenna is always pointing to the same spot in the sky. So like on any connection, you're prone to errors. Things will happen, interface errors, DNS issues. Remember that you cannot get to anything on the internet unless you have DNS. You saw on your assignment that you were trying to ping www.cisco.com, and what's the first thing that the computer did? Went to a DNS. Well, the DNS will resolve from the name to an IP, and once it gets that number, now your computer can work with that number. Your computer receives that information from the router and then says, okay, so now let me send this packet from my source IP to this destination IP. Layer 3 goes to the router goes, okay, I have a default route to go to my edge router, my border router, and then I go BGP to my ISP, and it goes BGP all over the internet until it gets to destination. And back and forth. So yeah, DNS can have issues. A routing misconfiguration, if it's not routing correctly, if the routing table is corrupted or the routing is static routes and those routes are no longer there, you're gonna have issues. Interference, yeah, it depends on your medium. If it's fiber, you're not gonna have that. If it's through air, like satellite, something like that, you can have interference. But that can happen. The book, I guess, assumes you're going to be using more of the Cisco equipment, but yeah, on Cisco, you have to go to what's called a privilege mode, not just log into the router, but you have to go into enable mode, which is a privilege mode. It's another password, not the regular. You log in with a password, and then you have an enable password that gets you into that privilege exec mode. And then you can show your running configuration or show run, or you show your interface configuration. I can show you that in class and how it is done on the Cisco router. But you can show your interface, and that will give you all the statistics of packet sends, packet receives, any errors, any drops, any disconnects. It will give you the speed of the connection. But that's where you can see also if you got any traffic. Case in point, last week we had a problem at the Homestead campus. My interface was up, but I could see the interface sending traffic out. But the inbound traffic, the input numbers were 0, meaning that I was sending traffic out, so the interface would see it, but I could not see anything on the inbound. But I was receiving nothing. There was zero bytes. So, and that was done through the show interface. I showed the specific interface, and I got those numbers. This is how it looks like when you do a show interface. I mean, you can do specific interfaces. You specify the fast Ethernet, in this case 00, and you see if it's up or down. And if towards the middle, you'll see that it says the input rate and the output rate. So they're both at 0, so there's no traffic on that interface. At the bottom of that red bracket, you'll see this, it says buffer failures, lost carriers. So all that information is there for you to troubleshoot. And continue with Cisco routers, you can do a show IP route, and that will give you the routing table of the whole routing table of the router. You can be very specific. It's a show IP route to this destination, show IP route to 4.2.2.2, and then it will show you how it is going to route to that, which is the next hop that it's going to use. Now I can log in into that other router, whatever the next hop is, and then go into that one and say, okay, now from you, if I'm going to go to 4.2.2, which route are you going to take? And then you start like going like that one by one until you see it. If you do a trace route, we can use that also on the router. Then trace route will show you all the hops that it's taken to get out. But on the routing issue, you can do a show IP route and say, okay, if I'm going to go from here, where are you going to send it? Now, it's not shown here, but you can do on a router, which is a better way to do it, is that the router is the one that has all the gateways configured, right? So on a Cisco router, you can do a show IP route, and you tell them who is the source. That's a source set for this from this network, from the 147.70.40.1, source it from that IP address, and the destination is going to be 4.2.2.2. How will you route that traffic? And sometimes you will see that it will show something different, because if you don't specify the source, the router will use its own IP address as the source. But you can actually specify a specific source and say, no, source it from this network, and then show me which route you take from this source to this destination. And sometimes that could be different. So I'll give you a little bit more insight. So this is how a routing table would look like. I see an error, but I'll tell you at the end. So you see that your 192.168.43.0/24 is variable subnetted. Remember VLSM? Variable length subnet mask, so that you break it into multiple pieces. So you see /30s, /29s, and some /28s. For the first one, the 43.0/30 is directly connected on interface 40. And then the other networks, the next two, the 43.4 and 43.8, is actually seen through a 43.2 and 43.2 through another interface 40. So the same interface 40, but it's a hop away because it has to go through that too. And then 43.16/29 is directly connected to a sub interface on 00.3, and then the other one is on a sub interface called 00.2. And 43.32 is on your fast Ethernet 10. And I like that. You see how is that? What I don't see here is a default route. You see in the middle by itself, it says gateway or last resource is not set, meaning that if something is not on this routing table, the router is just going to discard the packets. It doesn't know. It only knows all these 192.168.43 networks, and everything else is going to drop completely. Forget the packets, throw them into an empty bucket, and they will just sit there. It will just like lose the information because it's no gateway or last resort, which is your default gateway. Says, okay, if it's not on this table, send it to this other router, and that router will know where to go. So this router, I guess, is running by itself, or one of this is the connection, just internal connections. But anything else but these IP addresses will not route out of this router because there's no gateway or last resort. And that's the end of the chapter with module 9. We'll go through a lot of this in class to show you some stuff on the router itself, some of the BGP, how things are connected. Maybe I can go to one of those OSPF sites. I think I can, and bring one of the sites so you can, not completely, but bring one connection, so you can see the reconvergence of the routing table. But routing is interesting. It's a whole world of networking. I encourage you to learn more about routing, practice routing. If you can do anything with routing, to learn more, it will be very, very beneficial professionally. If you know more of routing protocols, if you learn OSPF or how ISIS is configured, how you control that, by all means, BGP. If you need to work with a company that's going to be connected to the internet, BGP is the way to go. And if you know that and how to control BGP routes, you will be an asset to that company. So, you can set up a lab at home to do BGP. There are many ways to do labs like that, simulate a network. So, but routing protocols is something that it's always a plus if you know it in this type of industry. Well, thank you very much.